In this video, we will discuss in detail how we can compute the exact Kohn Sham potential if we are given the exact density. This can help us to investigate what features of the exchange correlation potential are for exactly solvable systems, thus motivating and inspiring us when developing approximations. We will consider the example we have seen previously, a one-dimensional harmonic potential well containing just two electrons of the same spin. As we have seen, this system is simple enough for us to be able to solve numerically the Schrödinger equation exactly, and thus compute the exact density. This is the target density we require for our Kohn Sham system of non-interacting electrons to reproduce. It tells us the charge density at every point x in our one-dimensional space. We begin by writing down the Kohn Sham equations in one dimension, where we would like to determine what Kohn Sham potential is required such that the Kohn Sham density is exactly equal to the target interacting density. We begin by making a guess. We guess that the Kohn Sham potential is just the external potential of the real system. When we solve the Kohn Sham equations using this potential, we get a density that is different to the target density. We see that the Kohn Sham density is very different to that of the real system, as currently we have not accounted for any interaction effects. We will now define an iterative algorithm to home in on the exact Kohn Sham potential. We will adjust the value of the Kohn Sham potential at every point in space x by the difference between the Kohn Sham density and the target density. This will simply raise the potential where a density is too large, pushing charge away from that point, and lower the potential where the density is too small, pulling charge to that point. We will see this iterative equation has a fixed point where the Kohn Sham and target density are the same, as the adjustment to the Kohn Sham potential is 0. We multiply this difference by a mixing parameter mu to make the algorithm more stable. It ensures that we slowly approach the exact Kohn Sham potential and not oscillate wildly around the solution. We also raise the densities to a power called p. This is also a stability parameter. It ensures that the algorithm focuses its attention on the regions of the system of very small density. Choosing a small value of p is needed to get the fine details of the density correct in a reasonable time. It's worth noting that the values of mu and p do not change the final result, just how stably and efficiently the algorithm searches for the exact Kohn Sham potential. Let's perform one step of this algorithm. We see that a small bump appears in between the electrons. We will now see how this changes the Kohn Sham density by solving the Kohn Sham equations with this new potential. We see that the effect of this change of the density was to push the electrons slightly apart. Let us now perform the second iteration and can compute the new Kohn Sham potential. We see that the bump has grown larger. This algorithm is raising this bump to move charge away from the center of the system, as the Kohn Sham density is too large in this region. We will then update the density. We see a further separation of the electrons and subtle adjustments to the decay of the density towards the edges of the system. We can then observe the third iteration. We see again that the Kohn Sham density is getting closer to the target interacting density. We can then set the algorithm running quickly and see the effect of hundreds of iterations as it reaches convergence. We see that the potential is adjusted everywhere by the algorithm until the Kohn Sham density matches the target density exactly. This converged potential is then the exact Kohn Sham potential for this system by definition. We will now look at how we will extract the exact exchange correlation potential. We first remove the external potential of the real system, resulting in the Hartree exchange correlation potential. We know the exact Hartree potential for this system as we know the exact density. We then also remove this part, leaving only the exchange correlation part remaining. This is the potential that must be approximated when performing Kohn Sham theory. Next time, we will focus on exactly how we make approximations to this exchange correlation potential.